this video, we're going to go over a couple of the important features of water and some information about acids and bases. So first, we're going to talk about water's relationship with temperature. Water is very slow to change its temperature. So it has a stabilizing effect on temperature. I'll tell you a story to illustrate this. Here in the Midwest, we have plenty of humidity and there's lakes and rivers, there's water all around. So think about a summer day when the temperature is like 95 degrees, a hot summer day. At night, you would expect the temperature to be in maybe the 70s or 80s. So the temperature doesn't drop that much at night. In the desert, where the air is very dry and water is scarce, during the day, it can be 95 degrees. Now, I know this because when I was in college, I took a trip to the desert in Texas, the Chihuahuan Desert in the west and southern part of Texas, and we camped there. And during the day, it was in the 90s. At night, we froze. As soon as the sun went down, the temperature was in the 20s. So because there's no water there to stabilize the temperature would drop 70 degrees as soon as the sun went down. In your body, this is important because it helps keep your body at a stable temperature. When you exercise and you make lots of heat, the water helps stabilize your body temperature. Or when you go out in the cold, again, the water helps stabilize your body temperature. A couple of fun things you can do to illustrate how water stabilizes temperature. One of them with the balloons I do in class. Take a balloon and fill it with water. Now hold it over a lighter. The balloon won't pop. The water stabilizes the temperature and protects the balloon. Another neat thing, next time you're sitting around a bonfire on a nice fall evening, get one of those styrofoam cups from the gas station. Fill it with water. You can set it in the bonfire and it'll be fine because the water stabilizes the temperature and protects that styrofoam cup. If you throw an empty styrofoam cup into the bonfire, it will instantly melt and disappear. Another thing about water's relationship with temperature is that water cools any surface it evaporates from. This is why sweat cools you down. You sweat, you make your skin wet, then when that sweat evaporates, it cools your skin. Now, the key though is that the sweat has to evaporate. So around here where we have high humidity, the humidity interferes with the ability of sweat to evaporate, and that's why on that 95-degree summer day, you're sweaty and you're hot and miserable. When I was in the desert that time and it was in the 90s, we never really felt hot and miserable because your sweat evaporates and it cools you off. A demonstration you can do with this is get a terracotta flower pot. Get it wet and then let that water evaporate. And if you touch the flower pot, you'll see it feels very cool because the water is evaporating and cooling the terracotta pot. Another important feature of water is that it is a solvent. So molecules will dissolve in it. So we have two different processes that we're going to go over. There's dissolve and there's dissociate. Dissolve means that a substance mixes with water. And it forms hydrogen bonds with water. But the molecule remains intact. An example of this is glucose. The chemical formula of glucose is C6H12O6. If we have a beaker of water, so here's our beaker, and we have all these water molecules in here. Remember, they look like Mickey Mouse. And we'll just use a green G to represent glucose. If you put glucose in here, it will form hydrogen bonds with the water. But the glucose molecule remains intact. You still have C6H12O6. That's what it means to dissolve. Electrolytes are salts that dissociate in water. So this means that the molecule breaks apart or dissociates. The atoms detach from each other. And when this happens, you get ions. We saw this earlier when we were talking about sodium and chloride. Let's say we have some sodium chloride, some table salt, and you have a beaker of water. If we put sodium chloride into this beaker of water, the sodium and the chloride separate from each other. So remember, the sodium is going to form a hydrogen bond with the negative oxygen end of a water molecule, and the chloride will form a hydrogen bond with the positive hydrogen end of a water molecule. You no longer have salt. Instead, you get sodium ions and chloride ions. They're not bonded to each other as a molecule of salt anymore. Up here with the glucose, you still have glucose. So electrolytes will break apart and produce ions. And examples of important electrolytes. These are very important in the body. Think about Gatorade. It replaces your electrolytes. Think about somebody who's been sick with vomiting or diarrhea. They need Pedialyte to replace their electrolytes. So electrolytes are important in the body. So when you eat food, your food contains various types of salts. What we call table salt is just one example of salt. There's actually many different types of salts that we consume. So you eat salts, and then they dissociate once they are in the water in your body. And you get things like sodium, chloride, you get calcium, you get potassium, magnesium. These are just a few examples of important ions that you get from electrolytes that dissociate in the water in your body. Another important thing to consider now is acids and bases. We think a little more about water. If you have a water molecule, it has the oxygen and the 2 hydrogens. Water molecules will dissociate. And they just do this randomly on their own. They dissociate. So remember, dissociate means that the atoms in a molecule break apart from each other. So one of the hydrogens breaks off. It's over here by itself now. Now think back to when we learned about the polar covalent bond. The hydrogen is loaning its electron to oxygen. When the hydrogen breaks off, oxygen keeps the electron. So that means hydrogen breaks off and it does not take its electron with it. That makes hydrogen have a positive charge because it has that 1 proton, but it has 0 electrons because it left its electron with oxygen. This part, the oxygen and the 1 hydrogen, has a negative charge because it kept that electron. This is hydroxide. It's written OH minus, and you call it hydroxide. This one, we write it as H plus, and we call it hydrogen ion. If you have pure water, nothing else in it, whenever a molecule dissociates, you'll get 1 hydroxide and 1 hydrogen. So the ratio, if we count these and compare them to each other, we're going to put H plus in brackets here. That means concentration of hydrogen will be equal to the concentration of hydroxide. If we come up here and we look here at neutral, neutral solution is pure water. Okay, look at the hydrogens and hydroxides. There are 4 of each. So in pure water, hydrogen is equal to hydroxide. This is neutral, and neutral is 7 on the pH scale. It's right in the middle. If we talk about acids, an acid is any substance that when you mix it with water, it increases the hydrogen. So an acid donates hydrogens when mixed with water. So if we look at the acidic solution here, notice with the hydrogens, we have 6 of them. And with the hydroxides, there are 2. So in an acid, hydrogen is greater than hydroxide. And the more hydrogen it donates, the stronger the acid. And the closer to 0 the pH is. So for example, if we look at hydrochloric acid and wine, the hydrochloric acid is the stronger acid because it donates more hydrogens. If you look at coffee, coffee has a pH of 5. Compare that to lemon juice with a pH of 2. Which one do you think donates more hydrogens between coffee and lemon juice? It's lemon juice. Lemon juice is the stronger acid. It's closer to 0. Its pH is 2, which is closer to 0 than coffee's pH of 5. So the lemon juice donates more hydrogen. What about milk versus coffee? Here, the milk's pH is 6.3 and the coffee is 5. So milk is a weak acid. It only donates a few hydrogens. Now let's look at base. A base is something that binds hydrogen. So if we look at the beaker here with the base, notice we only have 2 hydrogens and we have 6 hydroxides. So if you have a base, your hydrogen concentration is less than your hydroxide concentration. And bases go up to 14 on the scale. And the more hydrogen it binds, the stronger the base. And the closer to 14. So if we look at bleach and ammonia, ammonia binds more hydrogens than bleach. If you look here, sodium hydroxide is all the way at 14. That is our strongest base because it binds the most hydrogen. Okay, here's human blood at 7.4. This is very important, keeping your blood at 7.4. So one of the reasons that pH is important in the body is that you have to keep your blood at 7.4. If your pH were to change, if it were to get below 7 or above 7.8, you could die. That's getting into the fatal range. So you don't even have much room for movement. In fact, you need to stay 7.35 to 7.45 is the only safe range. So you're talking very small changes in pH. The reason this is so important is if it were to change, you would denature the proteins in your body. This basically makes your proteins not function anymore. And you cannot survive if your proteins don't function. So in order to keep your blood at 7.4, you have buffers, your lungs, and your kidneys all work to keep your blood 7.4. And that keeps you alive and healthy.